Find the time, in seconds, needed to decrease the velocity of the rocket sled. In this problem, a rocket sled travels with an initial velocity of 600 miles per hour. A scoop is then lowered into a water trough, which deflects the water away from the sled at the given angle, theta. We're also provided the mass of the rocket sled. Assuming there is no thrust from the rocket, how long will it take to bring the sled to slow down to its final velocity, Vf? From Newton's second law of motion, we know the force exerted on a solid body, F, equals its mass times the acceleration. If we isolate the acceleration term, a, and then equate the acceleration term to dv dt, and then isolate the term dt, then dt equals the mass times dv divided by the force. In this equation, the force refers to the hydraulic force which causes the sled to slow down. We'll call this force F jet. The mass, m, refers to the mass of the sled, m sled. At this point, we'll write out force F jet, which equals rho v naught a times v. In this equation, rho v naught a refers to the mass flow rate of the fluid, m dot, and v refers to the velocity of the fluid as seen by the rocket sled. Since the water is not moving in the trough, these two velocities are the same and equal the velocity of the sled. Therefore, we'll write out the equation for F jet as rho v squared a. This particular equation is only true for our sled if theta equals 90 degrees. However, since the fluid is being redirected at an angle, we shall add the term 1 plus cosine theta to the F jet equation. Next, we'll plug in this value for F jet, and then take the integral of the left-hand side of the equation with respect to time, and take the integral of the right-hand side of the equation with respect to velocity. On the right-hand side of the equation, most of the terms are constant with respect to velocity and can be removed from inside the integral sign. After integrating, we're left with our equation for time. The problem statement provides us with the mass of the sled as 10,000 pounds. The angle, theta, equals 30 degrees. And we also know the final and initial velocities. We'll convert these velocities from miles per hour to feet per second by converting miles to feet and converting hours to seconds. Our revised initial and final velocities are rewritten and plugged into the equation. Since the fluid is water, we'll use a density of 62.4 pounds mass per cubic foot. The last variable in the equation is A, the cross-sectional area of the scoop, which can be determined by multiplying the width of the scoop by the depth of the scoop in the water. 6 inches times 3 inches equals 18 inches squared, which is the same as 0.125 feet squared. Now that we've calculated all the input variables, the time it takes the rocket sled to slow down equals 22.6 seconds. When reviewing the possible solutions, the answer is B.